Okay, so today we're going deep on something that's it's pretty fundamental to the whole AI landscape right now, transformer networks.
Yeah,
You see them
transformers.
everywhere.
They're everywhere and they're powerful.
Yeah, they power a lot of the really cool stuff that we see, but at the core of these things is this concept of attention.
Right.
The model's ability to kind of like zero in on what really matters in all this data that it's processing.
Hmm.
We kind of take it for granted, we see it working, but the way that that attention layer actually learns, how it optimizes itself during training.
It feels like a black box.
It's like total mystery. Yeah.
Totally. And for all of you out there, whether you're knee deep in these models every day or just trying to stay ahead of the curve, getting a grasp on the innovations behind how these models actually learn, that's crucial. And we got to go beyond just, oh, look, it works.
Exactly. Yeah. Yeah.
Why? How?
So that's our mission in this deep dive. We're going to unpack a recent research paper.
Okay.
This paper is called 2308.16898v3.pdf.
All right.
Bit of a mouthful.
Catchy.
Yeah, catchy title, but it really pulls back the curtain on the optimization process and some of the inherent, I guess, biases or tendencies within transformer attention. Think of it like getting a more rigorous, almost like an engineering levels understanding of how attention actually achieves these incredible things that we see.
Mm-hmm. A blueprint, so to speak.
Yeah, yeah, a blueprint, exactly.
And to give you a little roadmap, the research really zeroes in on two primary ways that attention can be, as they call it, parameterized or set up.
Okay.
The first one is what they call parameterization, where you've got a single weight matrix that essentially determines those assumption scores.
Mm-hmm.
And then the other way is KQ parameterization.
Okay.
And that uses two sets of weight matrices, one for keys and one for queries.
All right.
They kind of work together to calculate those same attention scores, but it's a different setup. And these, seemingly small changes can really have a big impact on how the learning unfolds.
So that's interesting. We have two different ways of setting up the same basic idea, but the learning process might be wildly different depending on which one you choose.
Exactly. It gets pretty deep pretty fast.
Okay, so let's unpack this starting point then. The researchers make this really interesting connection to something that a lot of folks in the machine learning world might have encountered. Support vector machines, or SVMs.
Yeah, SVMs.
Kind of a classic.
Classic. Good old-fashioned machine learning.
And they draw this parallel between optimizing the attention layer and a specific kind of SVM problem. They actually call it ATSVM, very creative naming there.
Very descriptive.
Yeah, and it focuses on achieving this maximum margin of separation.
Right, which is like, a key idea in SVMs, this idea of finding the best boundary between different classes of data.
So help me understand this. How does this, classic SVM concept tie into this attention mechanism in transformers?
Well, what's really innovative here is that they're reframing the entire attention learning problem through the lens of this ad-SVM.
Okay.
So when we're talking about cross-attention, where the model's comparing two different sets of information, the objective of ACT-SVM becomes very clear. It's about finding the best way to pick out the most relevant piece of information from the input, like the most important token, and separate it from all the other less important stuff.
So it's like picking the signal out of the noise.
Exactly. And this whole process, the way it learns to do this separation, is guided by the task we're trying to solve, the labels that we're using during training.
Okay, so it's not just about assigning weights to things. It's about finding the most robust, most clear way to actually filter out the information that matters.
Precisely. It's finding the best boundary. And this isn't just, some theoretical idea they came up with. The researchers actually went and did experiments.
Okay.
And they showed that this connection to AD-SVM isn't just an analogy. It has real practical implications for how these models learn and perform in the real world.
It actually affects the results.
It actually affects the results, which is really cool.
That's awesome. So it's not just a theoretical curiosity, it actually changes how the model operates in practice.
Right. It gives us a new, more fundamental way to analyze attention through this lens of optimization and margins.
Okay, so now that we have a sense of, I guess, the goal of the attention mechanism, let's talk about how these models actually learn, how they get to that point of being able to do this separation so well. And a big part of that is gradient descent, right? Often abbreviated as GD.
Right, GD.
The algorithm that kind of nudges the model in the right direction during training to improve its performance. So how does this GD, this gradient descent, operate on these attention weights under the W and KQ parameterizations that we talked about earlier?
All right, so this is where things get really interesting, and we start to see some of the more, I guess, subtle innovations that this research brings to light.
Okay.
One of the key concepts is global convergence.
Global convergence.
Ideally, we want GD, this gradient descent process, to find the absolute best way to select those crucial tokens, the important ones, to perfectly mirror the solution that we get from our ITSVM problem. Like, imagine you're trying to find true north on a compass, right?
You want to get to the exact right spot.
Exactly.
No detours.
No detours. You want to get straight there. So the question is, are there conditions under which we can be absolutely sure that gradient descent will actually hit that true north?
Right, because with any kind of learning algorithm, oh, wait, someone wants to join. Hey, go for it.
Based on this work, I can consider this work just add the attention to the SVM. So the novelty of this work just is the using the attention.
That's a really interesting point. You're focusing on how the attention mechanism connects to the selection of the most important components, like the optimal input tokens the paper mentions, right? It's about highlighting those key signals amidst everything else.
Exactly. And you're hitting...
Oh, go for it.
Does this work add the attention to the SVM as their novelty?
Absolutely. You've nailed it. The real novelty here is precisely that connection they're making.
Yeah, you're right. That's the core contribution, framing attention's learning process through the lens of support vector machine.
It's about understanding how attention learns to pick out the best information, almost like an SVM separates different classes of data.
Okay, so building on that idea of a good initial gradient that we were just talking about.
Ah, the dreaded assumption C.
But it's actually not that scary. It essentially means that the very first adjustments that the model makes, those initial steps, are already pointing in the general direction of that optimal solution.
Okay, so it's like if you're starting a hike and you're already on a trail that's heading towards the summit, you're in good shape.
Exactly. You're already on the right path.
But what happens if we don't have that perfect starting point? What if our initial gradient isn't quite so good?
Well, that's where we get into the concept of local optimality.
Okay, local optimality.
So gradient descent might find a way to select tokens that's pretty good, pretty effective, but it might not be the absolute best solution out there.
Right, so it's like getting to the top of a hill and thinking you've reached the highest point, but then realizing, oh wait, there's an even taller mountain just behind this one.
Exactly. And this can happen when a particular token, its importance score, is higher than the scores of other tokens that are kind of nearby in the model's internal representation. Like the model thinks this token is the most important in its local neighborhood, but it might be missing the bigger picture.
Oh, yeah, uh-huh.
Okay, that's a great suggestion. Let's jump right to the key takeaways and the real novelty of this research.
Absolutely. So to put it simply, the groundbreaking part of this paper is really establishing a formal link between how attention mechanisms in transformer networks learn and the principles behind support vector machines.
Yeah, it's this connection that's really the core contribution. They're showing that training the attention layer can be viewed as trying to solve a specific type of SVM problem, which they've cleverly named at SVM.
And what's fascinating here is that this isn't just a loose analogy. The researchers provide rigorous theoretical backing and experimental evidence to support this equivalence.
Right. They delve into the optimization process, specifically gradient descent, and analyze how it behaved when training attention weights under different parameterizations, the W and KQ setups we talked about earlier.
And one of the key findings is that these different ways of setting up the attention weights actually lead to different implicit biases during learning.
Exactly. For instance, they show that with KQ parameterization, there's a tendency towards solutions that are low rank, meaning they're more efficient in their representation.
And with the W parameterization, the bias is more towards keeping the overall magnitude of the weights relatively small, promoting a kind of simplicity.
Another major takeaway is the introduction of the generalized SVM, or Gen SVM. This extends the initial framework to handle situations where the most informative output comes from considering multiple tokens together, not just a single one.
Which is a much more realistic scenario for a lot of complex tasks. And they also explore how these ideas extend to sequential data and even to causal attention, which is crucial in language models.
So in essence, this research provides a new and more fundamental way to understand the inner workings of attention mechanisms. It moves us beyond just seeing that they work and starts to explain why and how they learn so effectively.
It gives us a more precise, optimization-focused lens through which to analyze these crucial components of modern AI.
And it opens up a lot of interesting avenues for future research, like designing even better architectures and training methods based on this deeper understanding.
Absolutely. The paper itself lays out several open questions that are still ripe for exploration.
So if you're keen to delve into the specifics, definitely check out the full paper.
It's a valuable contribution to the field.
We hope this wrap-up gave you a good sense of the key innovations and main takeaways from this research.
Thanks for guiding us there, and thank you for joining us today for this insightful discussion. We hope you found it valuable.
Until next time, keep exploring.
Bye for now.